Alright, welcome to this video about the three Riemann sum problems. We've got a problem where the information that is given to us is given by a graph, one where it's given by a table, and one where it's given by a function, an equation. So first we're going to start with the graph. So let's see, let me come down here just a little bit so we can actually see problem number one. So we have a car travels along a road at a velocity of v of t, where v of t is measured in meters per second and t is measured in seconds. A graph of v of t for time between 0 and 24 is shown below. So this, the y-axis over here is our meters per second. So I'm going to go meters per second. So I'm just going to write that over here just so you can remember. And our x-axis is seconds. So this is, come over here and put seconds on the x-axis, or I guess I should say the t-axis, the horizontal axis is measured in seconds. All right, problem number one. Approximate the total distance traveled by the car from time equals 0 to time equals 14 using a left Riemann sum of 7 subintervals of equal length. All right, so we're just going from 0 only to 14, so we're not worried about this space over here. We're just trying to approximate the area between the curve here and the horizontal axis. All right, we're going to be using a left Riemann sum of 7 subintervals. So first, let's see, we've got from 0 to 14, it's 14 units. If I were to divide that into 7 equal pieces, each of my partitions or subintervals is going to be 2 units long. So, and here we go. This is where it gets tricky drawing. Here we go. Whoa. That's not too bad. Anyways, it's supposed to be as straight. It keeps getting lower and lower. Okay, so there's that, and then 2 units is how far apart each of our intervals are going to be. They have to be of equal length as per the directions. All right, the left Riemann sum deals with rectangles, and we determine how tall so each of these is the bottom of a rectangle. So I've got 7 rectangles here, and each of them I determine how tall they are based on what kind of Riemann sum we were doing. So we were doing a left sum, which means I'm going to use the left side of each of these rectangles to determine how tall to make the rectangle. So let's start over here with this first rectangle. Here's the left side. I'm going to draw a line up until I reach my graph. Right there. And then I just come over straight across and draw my rectangle. Next one, same thing. So I'm going to come up until I reach my graph right about there, and then come over, and then come down, and then up. So just like that. Do that with each, and this one's going to be the same height. Do this with each of our rectangles. So this one also the same height. And up to here. And then finally our 7th and final rectangle right there. Alright, and you'll notice that some of these, so as I approximate this, some of these are going to be an underestimate. So you'll notice over here where I've got a positive slope, the left-hand sum is going to be an underestimate. And over here where I have a horizontal slope, slope of 0, it's going to be, in this case, perfect. But when I have a negative slope, as you see our function right there, I'm going to have an overestimation. So now we want to find the area of each of these rectangles and add them all up. So this first rectangle, it is 2 units by 6 units, so 2 times 6 is 12. 2 by 7.5, so that's going to be 15. 2 times 7.5 is 15. 2 by 9 is 18. 2 by 9 again is 18. 2 by 9 is 18. And 2 by 7 is 14. And 2 by 5 is 10. So what we have here is we've got 12 plus 15 plus 18 plus 18 plus 18 plus 14 plus 10 gives us, let's scroll down a little bit so we can see the area right here, an answer for problem number one of 105. Now let's think about the units for just a second. The way we found the area of these rectangles is we took this distance right here, which is measured in seconds. So for example, 2. So 2 seconds times this distance right here, which is 6 meters per second. So 6 meters per second. And what happens is when I multiply these together, I get 6 times 2 is 12, like we have up here, 12. But the seconds cancel out. And so I have 12 meters. So this is 12 meters, 15 meters, 18 meters. You add them all up and you get 105 meters. So that is the distance the car traveled from time equals 0 to time equals 14. That is it's also known as the change in position. So it's changed 105 meters. We don't know where it started from, but we know that from 0 to 14 it has changed by 105 meters. Okay, problem number 2. Let's take a look at this. It says, describe what is happening to the car on the interval from 0 to 14 at the point t equals 14 and from 14 to 24. So I'm not going to write in here. We'll just talk about it as we look up at the graph again about each of those things. So first, let's get rid of all this graph stuff. There we go. All right, so from 0 to 14, let's think about what is happening to the car. So the meters per second, this is its velocity. So it's got a positive velocity. It's traveling at 6 meters per second at time equals 0, and then by the time it gets to time equals 4, it's gone up to 9 meters per second. So it is increasing its velocity through here. So it's moving further away from the origin of wherever the position of 0 is at. Actually, I don't know if it's further away because we don't know where it's at. So it's just moving in the positive direction, okay, and it's increasing its velocity. Then at time equals 4, it maintains the same velocity, so it's traveling the same speed for 4 seconds. And then once it reaches time equals 8, it starts to, the velocity starts to go down. It starts to have negative acceleration. It starts to decelerate. So you can see it's slowing down, still going forward, but still slowing down, slowing down, slowing down. At 12, it slows down even faster, at a faster rate of change, until at time equals 14, the car comes to a complete and utter stop. The velocity is 0 meters per second. So that's what happens between 0 and 14. It's moving forward the whole time, speeding up, and then it hits the same speed, and then it slows down. Okay. Then at time equals 14, the car is at a complete stop. Then from 14 to 24, it's got a negative velocity, so now it is moving backwards. Perhaps it turned around or something, but it is now moving in the opposite direction. And it is gaining velocity, or I should say gaining speed. It's losing velocity. It has a more negative velocity. So it is moving faster and faster in the opposite direction until time equals 20, where it is now moving negative 3 meters per second constantly for 4 seconds. So it is moving back the way it had come. All right, let's take a look at problem number 3. It says calculate the area between the curve and the x-axis for each of the following intervals. So from 0 to 14 and 14 to 24. So it wants the exact area. So we're not approximating it. We want the exact area. So you can do this however you want to do it. I'm just going to, let's see, we'll do it in red this time. Actually, I want to do it in green. So let's see, we got, where is my little mouse? There it is. All right, so we've got this space right here. So I'm just going to kind of cut this in pieces so we can figure out how much area there is under here. I mean, you can just count the boxes if you want. But let's see, there's a triangle right there, there's a triangle right there, triangle right here. So I've got a whole bunch of little pieces here. Let's figure these out. This is 4 by 6, so this is 24. This is 4 by 3, so the rectangle would be 12. So cut that in half, would give me 6. 4 by 9 is 36. 4 by 5 is 20. 4 units by 4 units, so the rectangle would be 16. Half of that would be 8. And then here we've got 2 by 5, so that's 10, half of which is 5. So let's add all those up together. We get 6 and 24, so we're going to get 36, 8, 20, 99. So 99 meters is the area underneath this curve, between the curve and the x-axis. All right, now let's look at the other part. It asks us to also find the area under this curve over here, the exact area. So let's see, that's a triangle right there, rectangle right here. So this is 6 by 3, so that's 18, so half of which is 9. And we got 4 by 3, so that is 12 for a total of 21 meters. Okay, let's take a look at problem number 4. All right, so there's 3, so we came up with an answer of, 99 and 21. So question 4 says, according to the car's odometer, how far has it traveled? So it traveled 99 meters in one direction, and then it came backwards 21 meters. Now the car's odometer is just how far the total distance traveled. So it doesn't matter which direction you're moving, it just wants to know how far you've traveled. So this is going to be 99 plus 21 gives us 120 meters. That is the total distance the car traveled. 99 units forward, 21 units backward. Problem 5 says, how far is the car located at time equals 24 from its original location at time equals 0? So it went, as we discussed, 99 units in one direction, and then it came to a stop and turned around or went into reverse. We don't know for sure. But it started going the other direction, back the way it had come, 21 units. So we're going to do 99 minus 21, which gives us 78 meters from wherever it had originally started from. Now it is, by time equals 24, is now 78 meters away. Question number 6, let's go down here and look at this. This is question number 6. What does this tell us about the area beneath the x-axis? So let's go back up to the picture again. What kind of information does this tell us? And as we are figuring out the area underneath the curve, as we're thinking about time in this direction, so moving this direction, area above the curve counts as positive values. And once again, as we move in this direction, well, let's actually write it up here again. As I move in this direction, okay, area below the curve counts as negative values. And we got to be careful though, because, and it's kind of weird thinking about what do you mean moving in this direction? Well, what if I knew for a fact that when the car stopped, so let's pretend at this moment in time right here, when the car stopped for sure, I knew that the car was at a position of 200. Okay, I know that to be a fact. Okay, we'll just pretend. So at time equals 14, the car's position is at 200. Okay, so this would be our distance or our position of the car. Okay, well, now if I wanted to figure out where it ended up, so at time equals 24, I would take that 200 and it travels 21 meters in the the negative direction, so I would have 200 minus 21, which would give me a value of 179. So by the time it finishes, it would be at 179. So notice I did subtract. This counts as a negative value. I did subtract it. But what if we go in the opposite direction? What if we look at working this direction to the left? Okay, I know that the car traveled 99 meters from time equals 0 to time equals 14. So if I'm starting here and I'm working backwards, I need to subtract 99 from 200. So that way, so for example, that would give me at a position at time equals 0 to be at 101. That way, if I move this way again, 101, I add 99, I need to be up to 200. So what this tells us is if we work in this direction, that values above the axis count as negative values, values below the axis, if I'm working that direction, so like this, count as positive values. And we could see that too. If we had started here at 14 and we said, okay, yeah, I definitely at 24. At 24, we are definitely at a position of 179. Where are we at time equals 14? Well, I know I lost 21 meters to go from 14 to 24. So when I go from 24 to 14, I need to gain 21 meters. I need to add the 21. So 179 plus 21 gets us to 200. And then likewise, as we talked before, time equals 14, I'm at position 200. But this is not the velocity, this is just the position that we're at. And then in order to get back to 101, by the time I'm at 0, I need to subtract this value. So it depends on which way we are determining the area under the curve. So for our purposes here, we were going from 0 to 14, so we were moving from left to right. So the values above the curve are positive, and as we went from 14 to 24, values below the curve were negative. But just bear in mind that if we're working the other direction, if we're going from right to left, they swap. Okay, so now that's done with the graph. Let's take a look at the table problem. So down here we go. So notice this time we have a table instead of a graph. So let's see what it says. It says water is pumped into an empty tank by an electric pump at a rate of R of t, where R of t is measured in gallons per hour and t is measured in hours. Selected values of R of t are given in the table below. So it looks like we're going from time equals 0 to 8. So we said t is measured in hours, so this is a time span of 8 hours is going on here. And the R of t is the rate that water is coming, is being pumped into this tank. So let's just, for kicks and giggles, so let's say this is my tank, okay? And we have some sort of little spout right here, okay? And water is coming out of this spout at a rate of, whoa, that was not a very good arrow, at a rate of R of t, okay? And that's gallons per hour. Okay, and then water, is filling up. So how fast it's coming out? So at first it's coming out 4 gallons an hour. That's not a lot if you think about it. 4 gallons in an hour is not very fast, but that's all right. So it's pumping at 4 gallons an hour by time equals 1. So an hour later it's doing 7 gallons an hour. So it's doing more. By time equals 2, it's doing twice as much as it originally was doing. And so we can see that the rate keeps increasing until we get to time equals 5. That's when, according to our data, it reaches its, that's the highest that we know of. Now, we don't know for sure if this is the most it ever pumps out. For all we know, at 4.5, it spits out 15 gallons per hour, or at time equals 5.5, it spits out 15 gallons per hour. But for the data that we've been given, we know that at 5, it's 12 gallons per hour. So with the data we see, that's kind of the max value. And then we start decreasing. At time equals 6, we're lower. Until time equals 8, we're almost about where we started. 5 gallons per hour as opposed to 4 gallons per hour. So the important thing to remember with this table is we do not know what's happening inside these intervals. Maybe during every half hour the water turns off and the rate is 0. We have no idea. So this is the limited amount of information that we are given. So let's take a look at problem number 1. Approximate the number of gallons of water in the tank at time equals 8, using either a left Riemann sum or a right Riemann sum. There is no stipulation on how many subintervals you must use for this approximation. The solution key will use 4 subintervals of equal length, but you are welcome to use more or less, and their size does not need to be uniform. Okay, so this problem is just kind of play around with left sums, right sums, depending on how many subintervals you choose to have and their width. You're going to get a different answer than somebody else who might choose different characteristics, and that's okay. These are approximations. So I'm going to do what the solution key does, and I'm going to I'll do both. I'll do a left sum and a right sum. We're going to do 4 subintervals of equal length. Now, what a lot of people do is when they look at this table, they think, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, and they try to divvy that up, divide that by 8. And looking at a table and trying to divide it up I don't think is a very good idea. What I would do is I would turn the t-values into a number line. So I'm going to come down here and do my best to draw a nice little number line here. All right, so here is 0, 1, 2, 3, 4, 5, 6, 7, and 8. So there's my number line. And from there, it's a little bit easier to see how to divvy this up. You got 1, 2, 3, 4, 5, 6, 7, 8 little intervals here. Makes sense. 8 divided by 4 is 2. So we are going to make 4 subintervals of equal length, so they're each going to be 2. So here are my the bottoms of my rectangles right here. So I've got 4 rectangles. Now, if we do a left sum, so the green is going to be a left sum. We use as we did on the first problem, the graphing problem, we use the left side of a rectangle to determine how tall it is. So when I plug in 0, I get out a value of 4. So this thing is going to be, and I'm going to put a little note right here so I don't forget, that's going to be 4 units tall. Plug in, here's this next one. The left side is a t-value of 2, so I'm going to plug in 2. I get out 8. And let's see, 4 to 6, so we'll plug in 4, we get out 11. And this doesn't have to be too accurate. I mean, we're just using this to kind of help us gauge what it would kind of look like. 6 to 8, so 6 is the left-hand side, so a 9. This value right here is 9. It's right here, but that's okay. It's still the same height on this side. So 9. So we got 4, 8, 11, and 9. That's using the left sum. So we used 0, 2, 4, and 6. Notice I don't care about any of this other information. It's just those 4 values that I care about. So let's see what the area of each of these rectangles are. So 2 units by 4 units, that's going to be 8. 2 by 8 is going to be 16. 2 by 11 is going to be 22. And 2 by 9 is going to be 18 for a grand total of 64. So our estimate here, let's think about what this means in terms of the story. 64, we are estimating, remember this is gallons, that's a G, gallons per hour by the hour. Right? So when I multiply gallons per hour by hour, the hours cancel out and I'm left with gallons. So our guess, our estimate is that after 8 hours, we have 64 gallons inside of our tank. All right, so let's compare that with a right Riemann sum just to see what the difference is. There's still going to be 4 of them. They're going to be the same width apart. So even still, they're going to be 2 units apart. But this time, instead of the left side, we're going to use the right side of each rectangle to determine how tall it is. So this time, I'm going to be looking at 2 again. I'm going to look at 2 again, which, let's see, pumps out 8. So we're going to be looking at 4 again, which goes to 11. 6 again, which goes to 9. And this time, though, instead of using this one, we're going to use this guy over here. We're going to use 8. The time equals 8, we're at 5. So our first box is 2 by 8, which is 16. Then we've got 2 by 11, which is 22. Notice that those numbers just get shifted over. So I bet this one's going to be, next one's going to be 9. Our third one is 2. Oops, I put a 9 here. That's supposed to be 18. It's a good thing I can't count. Sorry about that. That's supposed to be an 18. It still is 64, though. I just got ahead of myself when I saw the 9. Anyway, so this is going to be 18. I'm like, how are we going to get 9? 2 by 9 is 18 for that one. And then 2 by 5 is 10 for a grand total of, so this is our right sum, grand total of 66 gallons. So they're both pretty close, 64, 66 gallons. Remember, this is just an approximation of what we think it is. Okay, let's take a look at question number 2. See if we can keep the table and the problem here on the same page. So approximate the number of gallons of water in the tank at time equals 8, this time using a midpoint Riemann sum. Use 4 subintervals of equal lengths. We're going to do the same thing we did up here, but this time with a midpoint sum. So let's do this. There we go. Got the table down here, so we can scroll all the way down here now, see the whole thing. Okay. So we've got, once again, let's draw our little number line. 0, 1, 2, 3, 4, 5, 6, 7, 8. There's a little number line. This really horrible line. It's all right. And we are breaking this up into 4 equal pieces again. So 1, 2, 3, 4. And this time we're doing a midpoint sum. So we want to use the middle of each interval to determine how tall it is. So not the left side, not the right side, but the middle. So this time, notice we're going to use 1. We didn't even use 1 at all up here. So we're going to use 1. It goes up to a value of 7. So we'll make a box, and we'll call that 7. 3 up to a value of 9. 5 goes up to 12, so somewhere up here. Remember, it doesn't have to be perfect. Just help. It's just a diagram to help us try to calculate the area. That's all it is. It doesn't matter how pretty it looks. 7, we go up to 6, and here is our midpoint sum. We use the midpoints of these to determine how tall they were. So this first one, we've got 2 by 7 is 14, 2 by 9 is 18, 2 by 12 is 24, and 2 by 6 is 12, for a grand total of 68 gallons is our estimate with the midpoint sum. Okay, that is our estimate of the number of gallons of water in the tank at time equals 8 using a midpoint sum. It's pretty close to our left and right sums as well. Okay, let's look at question 3. You can see it down here. I'll scroll down a little bit so we can see it. How would your answers to number 1 and number 2 change if the tank started with 5 gallons of water already in it instead of being empty? Well, let's come back up here and look at these. So our estimate, remember our table here is telling us how much the water is coming in. It told us at the very beginning, I don't know if you caught this in the explanation up here, but the water was going into an empty tank, and that meant at time equals 0, the amount of water in the tank was 0. There was no water in the tank. So when we calculated our approximations, 64 gallons with the left sum, 66 with the right sum, and 68 with the midpoint sum, we were calculating the change in the water level of the tank. So, for example, if there is no water in the tank to begin with, and our water level changes by 64, that's supposed to be a curly bracket, it's not very good, is it? Changes by 64 gallons from time equals 0 to 8. So now the water, is up here. Okay, that means there's 64 gallons in it. 0 plus 64 is 64. Well, this question 3 is saying, hey, what if instead of having no water to begin with, what if there was already 5 gallons of water in here? So we got 5. That means with our approximations, going back with the left-hand sum, that means instead of going from 0 to 5, we're still adding 64 gallons, but this time we're tacking it on to the 5. So now we would estimate to be 69 gallons of water in the tank. Remember, when we're working backwards, we're calculating the area. It's the change in the y value of our original function. It doesn't tell us where we're at. There could have been 100 gallons in here, and this answer and that answer and that answer would still all stay the same. These are all the same. Our approximations are all the same. All it is we take our approximation plus the initial value in order to determine how much water there is in the tank. So our approximation doesn't change. In this case, for problem number 3, it's saying we're changing our initial value. We're changing from 0 gallons to 5 gallons. So what's going to happen is our guesses of how much water is in the tank is going to go up by 5 gallons. But the approximation, all this stuff that we did here, does not change at all. All right, finally, let's take a look at what happens when we have an equation instead of a graph or a table. So this is problem number 1 on the function problem. It says a runner travels along a pathway at a velocity of v of t, where v of t is measured in meters per second, t is measured in seconds. The function v of t is defined as this little beast right here for 0 to 10. So it looks like our runner This equation is valid for 10 seconds. It says, number 1, approximate the total distance traveled by the runner from time equals 0 to time equals 10 using either a left or right Riemann sum and 5 subintervals of equal length. So let's do both. We're getting pretty good at these, so let's do both. So let's see. We've got 10 units. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And here's our, wow, didn't work very good. That's all right. There's our number line. And we'll get a second one there for our right Riemann sum. Probably should have not put this so close to that, but that's okay. So here we go. So we have 5 subintervals. We have a total interval of 10. So these are also going to be 2 units apart. So there's the bottom of my rectangles, and there are 5 of them. This is going to be our left sum. All right, so we need to plug in 0 to determine the height of this rectangle, 2 to determine the height of this one, 4, 6, and 8. Those are the numbers that we want to plug in. So we take our equation right here and we plug in 0 into here, and you can go ahead and do that on by hand or by your calculator, but we do get an answer of 4. Let me do that. Plug in 2 to get the left side of this rectangle. Plugging in 2 gives us an answer of 5.8. Plug in 4, and we get 4.8. Like I've said before, it doesn't matter what these look like, as long as you get enough, you draw them accurately enough that you can, tell the width and the height is all we're really trying to do. 6, plugging in 6 gives us 3.4. So this is 3.4, and finally plugging in 8 gives us another value of 4. All right, so now we just have to calculate the area. So we have 2 by 4, that's going to be 8. 2 by 5.8 is 11.6, then 9.6, then 6.8, and finally by 8. For a grand total of 44. This was meters per second. The x-axis was in seconds, so this is going to be 44 meters. That is our approximation for how far our little runner ran in 10 seconds, 44 meters. All right, same thing really quick with the right sum. Once again, 5 subintervals. So there's 1, 2, 3, 4, 5 subintervals of equal length, but this time we're using the right side to calculate how high it is. So 2, we know we get out a value of 5.8. 4, we get out a value of 4.8. Whoops, that kind of slipped down a little bit. That's okay, doesn't matter. 6, we get out a value of 3.4. It's funny. 8, we get out a value of 4. See if I can actually draw a rectangle. There we go. And then finally for 10, when we plug in 10, we get out a value of 9. It's probably a little exaggerated, but that's okay. So let's see our totals here. So we have 11.6, 9.6, 6.8, 8, and 18 for a grand total of 54 meters. So if we did a left sum, we'd come up with 44 meters. If we did a right sum, we'd come up with 54 meters. All right, number 2, we are approximating the total distance traveled by the runner from time equals 0 to 10 using a trapezoid Riemann sum and 5 subintervals of equal length. So let's get our same little scale here. And there it is right there. Okay, so we're doing a trapezoid sum this time. So still 5 subintervals of equal length, so they're still going to be 2 units apart. Like so. This time we have to figure out both the left and the right side of each of these. So if we plug in 0, we get out 4. Plug in 2, we get out 5.8. And that is our first trapezoid. Plug in 4. We're going to get out 4.8. There's our second trapezoid. Connect the dots. Plug in 6, and we get 3.4. Plug in 8, and we get out 4. And finally plug in 10, and we get out a value of 9. So there are our 5 trapezoids. Now to find the area of a trapezoid, the formula is you add your 2 bases together, so base 1 plus base 2, and you divide by 2. So you're finding the average of the bases, and then you times it by the height of your trapezoid. Now you got to be careful. The height of a trapezoid is the distance between your 2 parallel sides. So for our little figures right here, this distance right here is going to be our height. So our height on all of these are going to be 2. Base 1, base 2, or vice versa, doesn't matter. These are our 2 bases. The bases are the parallel sides. So we're going to have 4 plus 5.8 divided by 2. So that's going to give me the average height, times 2, oh that's beautiful, those are going to cancel out, plus 5.8 plus 4.8 divided by 2, times 2, also beautiful, plus 4.8 plus 3.4 divided by 2, times the height, which is 2, plus 3.4 plus 4 divided by 2, times the height, 2, and finally 4, I didn't mark that, 4 plus 9 divided by 2 times 2. So this is our formula for calculating the area. You do all of that work and you get an answer of 49 meters. So a little bit, I guess right in the middle of our other ones. Our left sum was 44, our right sum was 54, so right in the middle of those two. Okay, let's look at problem number 3 down here. It says, is your answer to number 1 an overestimation or an underestimation, and why? So for this guy, we've actually got to know what the graph looks like to kind of understand whether it's an overestimation or an underestimation. So I'm going to come down here, I'm going to go below here, and we're going to put what the actual graph looks like. So here's our graph. If you remember our left sum, was 44, right? 44 meters. Okay, and so I can quickly kind of sketch what our left sum rectangles would have actually looked like had we had a very accurate graph. Okay. And as we look at this, I mean, if it's hard to tell whether it's an overestimate or underestimate, that's fine. The important part is that we're trying to understand, you know, how good is our estimate. All right. So looking at this, I mean, we've got, if you think about right here, I mean, we're missing out on all that space. We're including this space right here and that space right there, which we probably shouldn't, we don't want to include, but you know, that kind of cancels that out right there. Then we got a little bit that we're not getting here, but we have a lot that we're not getting here. So I would say that this is going to be an underestimate. And you know, and that would make sense. I mean, we should be hitting around the right answer someplace, because with our right sum, let's write it right here, right sum, we were at 54, which is higher. So you know, and then our trapezoid sum, we were in the middle, we were at 49. So, you know, I would assume that this is probably going to be an underestimate, this is probably going to be an overestimate. So let's check it. So we'll just do the tops of these ones. So right there, yeah, we'll do the whole thing, why not? Now let's actually, you know what, let's do this. Let's just get rid of the green as well. There we go. So come back through with doing the right triangle, the right sum, I mean, right rectangles. I am tired. Okay, so there we go, right there. So this guy's an overestimate, this one's an underestimate, this one's an underestimate. Probably between the two of them, it would make up for that. This one is an overestimate for sure, and this one is definitely an overestimate. So I would say, you know, between these first, the the difference between these first three is probably close to 0. I mean, that's this space right in here is probably about the same as that space in there, so they'll cancel each other out. But we have all that extra space, so this is definitely an overestimate. And I think I mentioned this before, but if we're doing a right sum and you have increasing slopes, okay, you're going to have an overestimate. And you see here we have decreasing slopes. We're going to have an underestimate. Increasing slopes through here, so we're going to have overestimates there as well. So you know, this it's hard to say, you know, this function is mostly increasing or anything like that, but you can kind of see the difference. And then if it was a left-hand sum, the opposite would be true. Increasing values of our function would indicate underestimates, and decreasing would indicate overestimates. All right, so finally, let's take a look at number 4. It says, for what intervals are your trapezoids from number 2 overestimations and which are underestimations? All right, so let's come back down to this graph again. Let's get rid of our right sum material, and let's take a look at our trapezoids. So our trapezoid here, so here's our, the heights of the bases of our trapezoids, right? And let's see, this first trapezoid, when we connect these dots, that is going to be an underestimation, as is the next one. This third one, it's kind of hard to tell. It's pretty close. I think ultimately, though, it's probably going to be an overestimation. It's kind of hard to tell, though. This one is definitely an overestimation, and this one's definitely an overestimation. So the question is, for what intervals? So this one is going to be an underestimate, so 0 to 2. This one's an underestimate. This one is, gosh, it's kind of like breaking even. It's too close to call. We're going to call it too close to call. No, we're going to call it overestimation. Over, and over. Now you'll see a pattern here of when it's under and when it's an overestimate for the trapezoid. You'll notice that our function through here is concave down through about right there-ish, and you'll notice it causes the trapezoid to have an underestimation. It is concave up through there, and it causes our trapezoid to have an overestimation. That's why I ultimately decided that this one's probably going to be over, because I think my point of inflection is someplace in here. So it's mostly a concave up graph through there, which causes our trapezoid to have an overestimation. And that takes care of this video. So thanks for watching. Hopefully it made a little bit more sense. I'd say of all the things we talked about, some of the big things to keep in mind. Let's just come back up here to the beginning just really quick. This whole idea of when to add value and when to subtract value. So as we move from left to right, tops are positive, and then below the x-axis are negative, and working the other direction, they switch. That's an important concept to keep in mind. That was one of the things I was thinking of as I was going through this whole initial value stuff, where when we're approximating, we're not finding where the original function is located, like its position. We're just finding the change in the position. So as we talked about with this water in the tank, the change in water was 64 gallons. So if we didn't know how much was in there at the time, initially, we wouldn't know how much water there is in the tank. All we know is that it has increased by 64 gallons. So understanding that these approximations that we're doing, the area under the curve, is telling us the approximation or the full area is telling us our change in our y values, not not exactly where we're at, just how much it changes by. Knowing where we started from or where we're trying to get to is how we can figure out exactly how much water is in the tank or how far the car has traveled or things like that. Then let's see, what was the last stuff that we talked about? Just knowing these are approximations and that there will be some underestimate or overestimate is important too. All right, so that completes this video.